Hello again. Tonight we're going to talk about gravity wave communication, or how we can use gravity as a means of sending out signals and receiving signals. So we have to go to the basics. What is communication? I'm not talking about people-to-people communication. I'm talking about electronic communication. You need some way of encoding a signal on top of some kind of physics effect, something detectable at a distance. You need something that's going to encode the signal or modulate it and transmit it. That would be a sender. And then you need something that's going to receive it, filter it so that that's the only thing it receives, detects the signal, and then demodulates it. And now you have data going into the sender and then data coming out of the receiver. This basic concept of communication, sender modulating and receiver demodulating, that works on a number of different mediums. So electrical conductors like wires, from a simple telegraph, Morse code kind of thing, to something more complex like Ethernet local area networking. You can also do it in the electromagnetic spectrum, radio, infrared, visible light, in the atmosphere, out in space. The same techniques work. A sender that modulates some effect, and then the receiver that demodulates it, and you get the original data back. And you can even do it with acoustics, with sound. Simplistically, we do it by playing music. You can hear music and understand what the music is, but you can also have tonal patterns that are decoded. If you remember touch tone telephones, and for scuba, you can use underwater acoustic communication, hydrophones, that kind of thing. Now, once you have the ability to modulate information and send it and receive it and demodulate it, you can send all sorts of things: text, email, pictures, graphical images, documents. You can compress it to store a lot of stuff, compressed file folders and such, and all of that can be communicated on any of these mediums because you modulate it. You can do audio and video streaming, voice over IP, telephony, music. You've probably heard of MP3 for audio streaming and playing, and do the same thing for video with or without audio. Current ones are like H.264, 265 for communicating it, and what you're communicating is a video recorded as MPEG or MP4. So if you have the basics of, I've got something I can encode so I can modulate it, and then you can send it, and then something can receive it, detect the modulation, demodulate it, you get the original data back. So how fast and how much signal do you need? Depends upon what you want to send. If you want to send something low speed, remember Morse code? That was how many letters per minute can you send, which is by today's standards, very, very slow. So you go to higher and higher numbers of transitions or bits per second, and now you can send more information. But it's not just the information. You have to kind of put a wrapper around the information called a packet or a frame, and that will encode it. And then you have error detection, so you can tell if something goes wrong. You have error correction for fixing things that go wrong, small amounts. And then you need to send it out as a signal. But the thing that you're modulating, that effect, it needs to have a high enough distinction from the background noise, from just no signal present, a signal to noise ratio, an SNR. You've got to have it high enough so that you can detect the signal. And typically, whatever rate you want to send at, you actually need to send it at twice that rate, so you can tell, like, what is a bit, what is a single transition. And you do that simply by making the bits wider. And now anywhere within the width of 2 bits is where your signal is either high or low. And if you just want to send text messages, you don't need a very high bit rate. For example, submarines have one-way communication from their military base to the submarine way out at sea, using very low frequency communication, very low bit rate. It's actually seconds per bit, not bits per second. So not communicating audio or video via VLF, you're just communicating simple text messages. Now, if you want to communicate lots of information, like data files or video streams or things like that, you need millions to billions of bits per second. And that's where you see things like Wi-Fi 2.4 gigahertz. That's 2.4 billion cycles per second. And that's just the basic clocking rate. And then you use multiple of those clocks to make a bit and then a frame and then a packet, and you put all these protocols in place. So you need the billions per second to get to millions per second of usable data being communicated. So the essence of it is if we wanted to, say, communicate something, we would need a modulation technique of some effect, and then we'd need a sender, a receiver, and demodulation. As long as you can sufficiently reliably turn things off and on of this effect, you have a modulated signal. If the modulated signal can be detected as being there above noise, and that the symbols can be decoded from it in samples per second, there's this thing called the Nyquist-Shannon that says if you want X rate of change, you have to actually have 2X rate of change of the signal, so you can detect individual changes. If you have that, now you can detect it. But is that tying it to some specific sort of communication? No, actually, it's abstracted from the thing that you're modulating. If you wanted to send Morse code, you could send Morse code via smoke signals. That's an old way of doing things, but we found better ways of doing it. We use the electromagnetic spectrum or acoustics, and the EM spectrum includes both radio and light. We could use electrical signals on wires, the electromagnetic spectrum, or acoustics, and we can send higher amounts of data. That's what we do these days. If we find a way to produce gravity waves of a certain caliber, and we can receive them and decode them, now we have another means of communicating, and that is via gravity wave. That's in the future. So what are the shortcomings or corrections we need for particular kinds of modulation effects in mediums and such? Barrier penetration. You probably know that there are certain types of electromagnetic communication, like VHF radio, that don't go with the curvature of the Earth. They'll go straight, line of sight, and therefore, if you want to communicate farther than, I don't know, about 5 miles or so, your antenna's got to be high up and cover the area. So Earth curvature is the first barrier you have to how far you can communicate. And then the next one is the actual material that you're communicating through. In the case of radio, they actually use the ionosphere as a reflector for amateur radio communication. So they'll send the beam up to the atmosphere, bounce off of it, and now you can communicate very much farther away. Some radio frequencies don't penetrate certain things. If you're on higher frequencies, something as simple as a sheet of paper could block your radio transmission. If you come down to a lower frequency, now you need maybe a screen wire. This is called a Faraday shield. And if you get down to lower and lower frequencies, more and more can block it. And then curiously, something happens where if you get the wavelengths long enough, it'll penetrate cement walls, rebar, the atmosphere. And that's how we communicate using very long wavelengths. So that's how we can have a radio observatory on the Earth that can actually hear deep sky things way out in the cosmos, is because we're listening on low enough frequencies that it passes through the atmosphere. And then if you're using RF, the electromagnetic spectrum, you have dispersion. You send out a beam from an antenna and it widens out over the distance. So the farther and farther away you are, the weaker and weaker the signal is going to be. So you have to have a means of concentrating that. So if you ever looked at point-to-point radio communication, the sending radio antenna is small. The receiving radio antenna is multiple times that, like a dish antenna, parabolic dish, because the signal has so much dispersed over distance, you need to collect more of it to be able to detect it. And then you have to have a signal that's high enough in amplitude to get above any background noise or any radio frequency interference, whether it's natural from the cosmos or from the sun, or if it's artificial from just like, people putting noise out on your channel. So there's two ways you can deal with that. You can do what is known as band narrowing. If you think about radio receivers that can have things like filters, where I want to receive a particular frequency when I want to block out all the lower frequencies or all the higher frequencies, because they'll just be stuff I don't want to hear. Or wavelength filtering, you can have a very narrow band. You just want to hear the range of frequencies that you've transmitted. All the other stuff is just noise you isolated out. Now, that's not to say that makes a perfect medium for communication. The next thing you need is error detection and correction. And there's a thing called a checksum or a cyclic redundancy check, or a CRC. So whenever you send out a frame, like in Wi-Fi, there's a CRC at the end of the frame that says, if you take the bits that you received in the frame, and then you ones complement that, and then you compare that against the value of the CRC, it should be the same. Not any different by any amount, identical. That's your ability to detect whether or not the frame contains any bits that aren't right. And let's say you have a slightly noisier medium and you don't always get your frames correct. There are these additional things called error correction or Hamming codes, Reed-Shannon Hamming codes. And that allows you to recover a certain small number of bits. So if you wanted to recover, let's say, 3 bits that are in error, and they can be anywhere in the block, you're talking about RAM in a computer. That's called error correction memory, or ECC memory. It uses a Hamming code of a few bits to, if a bit happens to flip, you can detect it and then you can correct it. As you get to larger frames of deep space data, you want to correct up to 11 or 13 bits, and that's where you start getting into the Shannon codes to correct more bits, but the amount of correction information you have gets to be bigger. We used to use these sorts of codes on disk drives, on rotating media disk drives, because you would have hiccups and you weren't getting all the magnetic signal that you thought you were getting, so you would need correction codes. So what would be the essentials for gravity wave communications? Well, you need a modulator, a sender, a receiver, and a demodulator. So you need to be able to turn gravity waves off and on fast enough to send the amount of signal you want to send. You would need to have a strong enough gravity wave amplitude to be able to detect it above background noise. We have these things called interferometers that can detect gravity waves, but they have limits as to, it must be a strong signal, high amplitude, and the frequency or wavelength must be very long. The frequency must be very low and the wavelength must be very long, and gives us the better ability to, was that a gravity wave sinusoidal hump or not? So yes, we can detect gravity waves using interferometers, using pulsar networks, and it has to be a certain class. Anything outside of that, and it could be happening, we just never hear it. So we need the signal to be above the noise, and we need to be able to detect it at a fast enough rate that we can pick out the bits and demodulate it. How would you achieve that using gravity waves? Well, let's see. If you had a spherical reflector and it was suspended electromagnetically in a vacuum, you could use that as the transmitter if you had on the outside of that chamber a bunch of LEDs, a bunch of light emitting diodes, and you could selectively switch which ones you want to send and how bright they were. The reflection off of that inner sphere would cause a magnetic moment to shift. That's a very low amplitude, frequency could be high frequency, gravity wave. Not huge, but it would be a gravity wave. It doesn't have to be as big as the inertial dampeners in tall buildings. It can be small if you have a detector that's good enough. The angle at which you wanted to transmit your gravity wave, if you have the inner sphere and the outer sphere with the emitters on it, pick which emitter you want to go in which direction, and that would be the angle that you're going to be sending the gravity waves. How would you detect them? Well, you could actually use as something that would move something small to a detectable level. Now, this is not large, but has a low frequency, so you could send low rate text. I think a clever text to be sent is, Watson, come here, I need you. People that understand Bell and telephones might get that. So how would you detect it? We have these things called seismometers that can detect earthquakes. And the way they do that is they have the detector connected to the ground, but then the rest of the device is isolated from it. So the detector can move independent of it and record the difference between the thing that they're mounted on and then the ground below it. You can do a similar thing with an ultrasonic detector in a vacuum chamber. Again, vacuum comes into play. Medical devices that are ultrasonic detect ultrasonic waves. And the way that they do this is because the ultrasonic wave enters the receiver and causes an oscillation of a nanoscale little tongue sticking out inside of an electromagnetic field, and it causes a little flow of voltage. Well, you can use that if you have that pointed in a certain direction. Then when the gravity wave comes through, it would essentially move that little tongue that's inside the ultrasonic detector. But since it's in vacuum, it wouldn't be moving the entire detector or the device that's sitting on a table. It would only be moving that nanoscale little tongue sticking out in the magnetic field, and you get a voltage from it. So it would be a very low amplitude gravity wave. You'd need lots of low noise amplifier or amplification, and the frequency would be very long. So it's a specific kind of gravity wave. But if you know where you're sending from and you know where your receiver is, you can point the transmitter at the receiver and try a short distance initially, and then see if that simple text message could be detected. And you have a confirmation that gravity wave communication is technically, theoretically possible. So let's say you've never used a shortwave receiver and somebody gives you one, and then you start tuning it without understanding how many different radio senders there are out there and at different frequencies, different bands and such. So you start tuning things in, and all of a sudden you hear things that you can detect, like people speaking and such. And then you hear other things that are like, it's high-speed modulated data, and you're unable to comprehend what that stuff is. So it'd be like a transmitter communicating in something that is a foreign language that you can't understand, or computer data that is moving so fast you can't hear the individual bits. You're unable to detect it, to modulate it. If you have a receiver for gravity waves and you're able to start receiving things, you may be receiving gravity waves that are from an unknown source with an unknown modulation technique. It's not in any known language. How would you recognize it above artificially generated noise? And it's by the patterns in the noise. If the patterns are whistly, as let's say Jupiter's RF or the sun's RF or Saturn's RF, then those would sound naturally produced. But if it happens to have a recurring pattern to it and it's tight and it's high speed, that's artificially created. So you would notice if you suddenly started receiving gravity waves because you built a receiver and you go, what's this noise in the background? That noise may be gravity wave senders that have been sending for some time, and you just recently created yourself a receiver that can detect them. There's another thing called fish, where the fishing is good, or only looking where the light is better. So if the initial gravity wave communication was only with high amplitude signals or high signal to noise ratio using long wavelength, low frequency, or low samples per second, then there's some things that you would be able to communicate with, and other things that would just be out there. You can detect them. They sound artificial, but you don't know how to communicate with them. So if it's a random sound and you have no ability to decode it, it might be interesting to astrophysicists as cosmic noise. Kind of like cosmic noise in radio frequency is something interesting, but not useful for communicating data. But if it turns out that it's sounding natural, you may just go, well, we don't see anything extraterrestrial intelligence here, and it's not a simple modulation, and the modulation technique happens to use advanced modulation techniques. It may sound like it's a natural noise, but it's not, but you wouldn't know. But if you were using a particular medium like radio frequency, why would you ever use that low frequency signal? I can think of one-way deep submarine transmissions, but the mediums that we do use for communication for high bandwidth, we'll typically pick a very high frequency, like very high frequency, ultra high frequency, super high frequency, up and up and up and up. When we want to communicate with space probes out in space, we don't use megahertz signals. We use 8 to 10 gigahertz. That's billions of cycles per second as the base frequency that we then modulate data onto. And we've got lots of error correction and error detection in that. But we have to get the signal amplitude up high enough where we can digitally detect it above background noise. If you're thinking you're going to use a long wavelength, low frequency, not too high in amplitude gravity wave for general communication that would replace radio frequency communication, that's probably not happening anytime soon. You're probably going to have to develop more advanced forms of gravity wave transmission and reception at higher amplitudes, higher frequencies before it would become meaningful and maybe replace radio frequency. Will gravity waves eventually replace radio frequency, light, infrared, and visible? I think so. It's just going to take time. Remember, electromagnetic radiation, modulation of it replace smoke signals. You simply go with what's better. So if we're right now using radio because that's what's better, if someday gravity waves can be sent over longer distances more reliably out into deep space, especially if we start picking up artificial signals, then we're going to gravitate towards using gravity waves for communication. But we need to improve the data rates. If initially we're only seconds per bit, like VLF, that's fine for text just to prove out that it works, but it's not good for large files or voice or video. We need to get up into at least the megabits. We need to find ways to do the modulation, but there's already a bunch of different modulation techniques that we use for the electromagnetic spectrum, be it radio or light. We can just repurpose those. They're just bit encoding kinds of things. We need a transmitter that's going to be putting out enough amplitude, enough oomph in the gravity waves that we can detect it above background noise. And then our receiver needs to be able to pick that out. So we need sufficiently high sampling rate or samples per second, demodulate it. And, I think an ultrasonic detector in vacuum with a lot of low noise amplifier should be able to do it. So now you have a transmitter, a receiver, and a modulation technique. Once this video has been publicly produced, if you've got the resources, see what you can do. Lots of links as usual. Read Solomon codes is what it is. Comments? Question?
I think it's a good idea. It should be looked into because it's.
I think so. We gave up on smoke signals because radio communication was so much better. And as we went faster and faster and faster with the data communications, now it's our go-to for anything we want to send or receive. And I think once they realize it's possible to do it with gravity waves or gravitational waves, they're going to improve upon it. And once they get it to be practical at the millions of samples per second kind of rate, because it's going to be so much better than radio frequency modulation or modulation of the electromagnetic spectrum, it's just going to gradually replace it. But I think the most interesting thing is if we create a receiver and we start decoding things and we start hearing other transmissions, we may find that the universe gave up on radio a long time ago and has been using gravity wave for transmission modulation for a long time. But we won't know until we build a receiver.
Or something else that permeates the universe.
Yes, there's the potential for other things that are faster than the speed of light, but we don't really have a basis for the technology for that at this point. But gravity waves, we do. I had an email exchange with somebody who was knowledgeable of what LIGO was doing. And I said, would mass dampers in skyscrapers produce gravity waves? And he thought about it for a moment. He goes, yes, but they wouldn't be at the wavelength and amplitude that LIGO would be able to detect. But you know what LIGO can detect? Trucks driving by the LIGO facility.
It disturbs.
The vibration of the trucks in the asphalt actually produce gravity waves.
And the damn thing is so long, too. No, they got a small one, smaller than the 11 miles or whatever.
4 miles. They're 4 miles each direction.
Yeah, but there are smaller ones now.
There's actually even bigger ones. There's the pulsar timing array, or the PTAs. And what they're doing is they're measuring the incredible accuracy, the celestial natural beacons of pulsars, fast rotating neutron stars, and they measure when the beam comes by the Earth. And they can clock it down to, a nanosecond or so. And they now have receivers that can time that pulse down to a tenth of a nanosecond. That's, you're going from nanoseconds to picoseconds, and they can see that they vary by picoseconds within the, framework of nanoseconds. And they claim that to be gravity waves moving through the fabric of space-time between the pulsar and Earth. So if you have a gravity wave that's propagating transverse across that distance, it's going to expand and compress the space-time continuum, and the pulsar's timing will be off by a little bit. And the pulsar timing array, I think at last count, they had like 200 pulsars. So they're watching 200 pulsars three-dimensionally through space, and they can actually watch the gravity wave move through the cosmos. So we have receivers, but it's only if the amplitude is very high and the wavelength is very long, and then we can detect them using pulsar timing arrays. But yes, we need to make better instruments. And it just sort of clicked with me that the metamaterials they use to make ultrasonic receivers for like medical device transducers, those are extremely sensitive. And the way they work is there's a little conductive tongue that sticks out in kind of a U shape, and the U shape is conductive, and therefore you have metal inside of a metal conductive area, and that produces an electromagnetic field, and it induces a voltage on the stem of that tongue. And then we have amplifiers, low noise amplifiers, that can amplify the signal like 2 billion to 1, and it brings up the signal high enough, and now you can start to see the movement as the reception of the ultrasonic signal. So those are proven medical devices nowadays. So all you need to do is put that thing in a vacuum where there can't be any air motion, and then you isolate it from radio waves. And the only thing that's going to get in there and move that little tongue, gravity waves.
Yeah, you can also put a charge on that little tongue, and then
you can send them. Yeah.
Yeah.
That's how ultrasonic devices send ultrasonic pulses at 40 kilohertz. But that's just technology we have today available at commodity prices off of Amazon.
Goes on and on. Well,
Yeah.
lucky there's so many people in the world to work on these things. Yeah, it's true. Just think of the thousands and thousands of technicians working on these things.
Well, I look at it more as the advancements in technology are getting so far beyond the general population that it's indistinguishable from magic.
Getting pretty close. You know it.
Okay. Any other comments or questions before I stop recording? Hearing nothing.